This is the first video for the second portion of Power Series in BC Calculus. So this is technically the third video overall for Power Series. And in these videos for part two, we're going to be looking at how derivatives and integrals can actually help us when it comes to Power Series. So we're going to start with finding a Power Series by differentiation. So in this particular problem, and in a lot of these problems that are going to involve differentiation or integration, they will start by giving you the terms for a power series, for one particular power series, and then ask you about a different power series that's somehow related to the first one. So here on example 1, it says, given that 1 over 1 minus x is represented by the power series 1 plus x squared plus so on and so forth plus x to the n, where n is going to infinity, on the interval from -1 to 1, find a power series to represent 1 over 1 minus x quantity squared. So if they're giving you information about a series, then they're trying to say, hey, that one's going to help you with this 1 over 1 minus x squared. Because with the 1 over 1 minus x squared, we're not going to be able to manipulate that like we did back in part 1 to come up with that a over 1 minus r formula to then substitute into our sigma notation for the power series because of the way it's that 1 minus x being squared inside of there. So we have to use the other tools that we have, like its relationship to 1 over 1 minus x. Well, let's see what that relationship is. And given the fact that we're talking about derivatives, I'm thinking that maybe the derivative of 1 over 1 minus x might help here. So if we do the derivative of that, that's like doing the derivative of 1 minus x to the -1. So that would become -1 times 1 minus x to the -2 times the derivative of the inside. So we would actually end up with 1 over 1 minus x quantity squared. So how is that helpful? Well, if the two functions are related in the format that 1 over 1 minus x quantity squared is the derivative of 1 over 1 minus x, then that would mean that their power series are related the same way. So if I want the power series for 1 over 1 minus x quantity squared, I just need to take the derivative of the power series notation for 1 over 1 minus x. So you literally can go through and just do term by term derivatives. So the derivative of 1 is going to be 0. The derivative of x is going to be 1. The derivative of x squared is 2x. Now I would probably, figure out what this next term would be so that you could have 3 terms here at the beginning. That's just kind of standard practice. And then if we take the derivative of the x to the n term, that would bring the n to the front, and that would become x to the n minus 1. However, we like to have an x to the n term in all of our series. So what I would probably do again is I would come up to this original one and I would figure out what the next term is after x to the n. That would be x to the n plus 1. So its derivative would be n plus 1, and then it would be x to the n for that. And then I know I'm writing on top of my blue, but you can ignore it. Then we would put plus ... there. So that is the power series written out in expanded form for 1 over 1 minus x quantity squared. Now we also want to talk about the interval of convergence for it, since they gave us the interval of convergence for the original 1 over 1 minus x as -1 to 1. We could try to find the interval of convergence for 1 over 1 minus x quantity squared. Doing the same way, you could find the r, and then you could set it between -1 and 1. But if you look at the graphs of maybe the first few terms here, 1 plus 2x plus 3x squared, and 1 plus 2x plus 3x squared plus 4x to the third, increasing the terms that we're putting in for that function, then you'll notice that they are going to converge, or the graphs will be very similar to each other if it has the same interval of convergence. And we will actually discuss that further along in this video, but essentially, if a power series is created by taking the derivative of another power series, then it's going to inherit whatever the interval of convergence is for the original. So you don't even really have to think about it. You're just going to pull it off of the original power series interval of convergence. It'll have the same center, it'll have the same radius, all of that sort of stuff. Okay, so let's look at another one. It says use the given series and the function f of x that it represents to find a power series for f prime of x. Okay, so this is the power series for f of x. And looking at it, I noticed that another way I could write it is the sum from n equals 0 to infinity of 2x to the n. And that makes it a little bit easier to identify the fact that my r would be what's being raised to the nth power, and my a would be the coefficient there, so it would be a 1. So the function for this guy would be a over 1 minus r. So that's my f of x function. And then we want to come up with a power series for the derivative function. So with that, sometimes that means that they're looking for the function for the power series. Sometimes they're looking for the sigma notation for the power series. So what I would probably do is I would find both of them. So obviously finding the derivative of that, we would just use the quotient rule with 1 over 1 minus 2x. And so we would end up with 1 minus 2x times 0 minus 1 times negative 2 all over 1 minus 2x quantity squared, or 2 over 1 minus 2x quantity squared. So that is our derivative function. We then want to find the actual terms that would be in it. So what I would probably do is I would begin by taking the derivative of individual terms of my original 2x to the n series. So I'm going to come up with some terms by starting back up here with this notation and starting with n equals 0. So if I put 0 in for n, my first term is a 1. And then if I put 1 in for n, I get a 2x. And then I get 4x squared. And I'm going to go one more. So with a 3 in there, I get 8x cubed. And then with the n in there, I would have 2x to the n. The next term, because we kind of saw in the last problem that we want the n plus 1 in there as well. So that's what it would look like. So this is the power series then that I'm going to take the derivative of to get my f prime of x power series. So the derivative of 1 is 0, the derivative of 2x is 2, and we get plus 8x plus 24x squared plus dot 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 plus n times 2x to the n minus 1 plus n plus 1 times 2x to the n plus dot dot dot. Now, quite honestly, when they're asking you to find the power series for f prime of x, they usually are going to want the answer to be written in the same format as how the problem started. So our original function was written in that sigma notation, so we really should probably try to come up with sigma notation for my f prime of x. If you go look at the terms that you've written out, though, your sigma notation usually comes from that nth term. So it would just be n plus 1 times 2x to the n. So as long as you can figure out what the nth term is, then you know what you have what you need in order to write the sigma notation for the power series like that. Okay? Now, in terms of an interval of convergence, they didn't ask for it, but we could go back to the original problem because remember, once again, whatever the interval of convergence is for the original problem, that's also going to be the interval of convergence for the derivative power series. So the original problem had a common ratio of 2x, so my interval of convergence would be negative 1 is less than 2x is less than 1. Divide everything by 2. So your interval of convergence would be from negative 1/2 to positive 1/2, and that applies to both f of x and f prime of x. Okay, so that's going to wrap up the portion of the notes that cover term by term differentiation with power series. The next video is going to look at integration. with power series.